Okay, so this video is going to try and be like a cover-all on scatter diagrams. Not the most, not the topic with the most things involved with it, but it is quite an interesting topic, and I've got something interesting to show you at the end, so hopefully you stick around for that. Well, is there a trend in this data? The main thing we use scatter diagrams for is to evaluate trends, and by a trend I kind of mean like, is one going up with the other, or is one going down with the other? Hopefully from that you've kind of thought like, well, it's a bit hard to tell. There's a lot of numbers there. None of the ages are even in order. This is a terrible chart, whoever's made this. Well, one way we can kind of make it clearer is by plotting the graph. So we just we put age on the bottom, hours of exercise a week, and we'll have ordered this a lot better, and we'd have put 26 with 3. So by 26 you'd plot up and you'd plot 3, and so on and so forth. I can see 40 and 0 is there. And we were trying to find out is, as you get older, do you exercise more or less? Well, from this, what do you think? It seems like we're kind of going down a little bit. However, there's this one value there that doesn't seem to, kind of seems to stand out. When we have something like that that doesn't seem to follow the trend we're kind of expecting, if it's just one value, we call that an outlier. And sometimes we exclude that from our data if it kind of messes with it too much, and it could just be, I don't know, we could have interviewed an ex-Olympian or something like that who still does loads of exercise, and they didn't really follow the average sort of Joe of exercising. I would say that there's kind of a slight negative correlation here, and we like to use the word correlation when we're talking about scatter diagrams, and we'll get to that in a little bit. So, what kind of trend or pattern do these data contain? So we've got age, an hour of studying per week, an age of hour of studying per week again. So maybe we just interviewed different sets of people. Well, on this one on the right, it's really clear that as people get older and get into higher levels of education, so this might be a university stage, of course you're going to be studying a bit more. This is your A-levels, this is your GCSEs, and this is kind of your primary into the beginning of secondary. And it's showing a really clear positive correlation that as you get older you study more. There's no outliers or anything. This one's a little bit more random, but you can kind of see it's a very, very weak and positive correlation here. But it's like kind of the lower values are over here and the higher values are up there, so I'd say that there's some sort of trend. There's these 5 graphs and 5 tags. So if we were in class we'd drag them about. Can you pause the video and just see if you can kind of match these up with positive, strong positive, negative, strong negative, and no correlation? So a strong positive correlation is where we're kind of going up and to the right, and all of the data is very neatly tied around our line of best fit. So this one would be a strong positive correlation. The weak positive correlation is where it's going up and to the right, but so as one gets bigger, the other gets bigger. As people get older, more people study. That's kind of the sentence you'd write if you were trying to write it out. But it's not as tightly fit. It's kind of, they're loosely following the trend. Another easy one to do is our strong negative correlation. So as people get older, they're doing less of something. If we're talking about our studying, so as people get older, they do less hours of exercise. That could be one that would fit this. And this is all very closely knit around our line of best fit, so it would be a strong negative correlation. And then a weak negative correlation would be similar to this one above it, but we're going down, so as this increases, the other decreases. And they're not so closely fit around our line of best fit. And then a no correlation is the one where we don't bother drawing a line of best fit because there is none. This is just completely random, and we've kind of shown that these have no correlation at all, and they don't predict each other in any way. Another thing we could be asked to do is to construct a line of best fit, and when we construct a line of best fit, a lot of people mistake that they think it has to start here. in the origin, which is kind of the bottom left of your diagram, normally like 0, 0, but in this case 0, 10, or 10, 0. But that is not the case, because obviously we'd have no chance of drawing a line of best fit here, and if you started one there, then you'd have to do a really steep, and that kind of misses out all them beginning parts of the data. So it doesn't matter where it starts and ends. You want to try your best to get about half, to split the data in half, so half on top, half on bottom of the line. You'll see what I mean when I do this line. I'm going to go something roughly like that. I think that's kind of through the middle. And what I'm meaning is I've got like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values are below the line, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I could have done that slightly better, but you can see that was what I was going for, getting just about 50-50 on the top and bottom. And that one would show to be kind of a relatively strong negative correlation. And then this one here, this is a very strong positive correlation, and my line of best fit could be something like this. So if we look 1, 2, 3, 4, 5, 6, 7, 8, and then 1, 2, 3, 4, 5, 6. So again, I could have done slightly better. I could have nudged it a little bit more to the left, or to the right actually. But that's not the end of the world. But you just want to try your best to get it about 50-50, and if you can, then that's perfect. So true or false, if you can just answer these 3 questions. So we're going to go through them now. A line of best fit should always start at the origin. That is a false. As you can see, this one hasn't started at the origin. The origin is down here. That's the origin. But no, we don't have to. If there is no correlation, a line of best fit should not be drawn. That is true. If the points are all dotted all over the place and we can't draw a nice line between them, then we shouldn't bother, because it'll be more confusing. The line of best fit must have the same number of points above it and below it. This is kind of like a true, but it's not one that people are so strict on that if you get one more point above than below, they're going to say you're wrong and disregard all your research. Let's see what these guys have done. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 below, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So yeah, they've done it pretty well. Obviously an odd number, you can't do it bang on. So yeah, that's our some key points of a scatter diagram there. This is where it gets into the kind of the good stuff: interpolation and extrapolation. Interpolation is where we draw a line of best fit, and we're asked, well, what could we expect someone of 19 centimeters has a handspan of 19 centimeters? How tall would we expect them to be? So we go along to 19 on our handspan, and we go up to our line of best fit. And this is like a good estimate from all this other data, and then we'll go across and we'll say probably about 156. So 156 centimeters. And then if we have a look at we could go the other way, so 150 centimeters tall, what would their handspan be? So go across until we hit our graph and go down in the straightest line you can. Well, they're kind of almost 17. So we'll say almost 17 centimeters. To be honest, we can go, with it being centimeters and not age or anything like that, we can go a bit more detailed. I'd have said that's about 16.9. You're probably going to be allowed a few either way on your decimal places and stuff. But this is a really good estimate, and that is because it's within our data. Anything that we try and estimate that's within our smallest and largest values, we can say that that's a good estimate. An interpolation is a good estimate. Whereas when we go to extrapolation, we're going to be asked to find something that's not in our range of values. So we've found kind of people between 12 and 22 centimetre handspan. So if we're asked if someone's got a handspan of 5, well, you can see our line of best fit actually hasn't gone down this far, so we'd have to extend it. But we have no idea if this trend is going to continue. There's so many things in real life where a trend happens and then it can just change completely. So you might look at ice cream sales in the summer, and if you carry on that trend of increasing sales, you might think, well, October, November, December is going to be crazy for sales, but it obviously just drops off. That's more stuff you can predict. But if you kind of look at all the stuff in the stock markets, they're constantly going up and down. So if you don't have stuff, if you're trying to extrapolate and predict the future or predict the past or predict handspans of people outside of your data range, it's quite a dangerous thing to do. And you can't trust your data. You can't trust the data outside of your data. You have no idea what's going to happen. So in this case, what we would kind of guess that they would be about 131. So somewhere here. And then if someone has a handspan of 30 centimeters, so we'd have to extend this again. So 30 centimeters would say about 176 centimeters. But again, we can't trust them. We can't trust this. This is just a very, very bad estimate. For the reason of, I don't know, the example I like to use is the death rate kind of before World War II. No one would have predicted that the death rate would have gone shot up. It was probably coming down and down and down, and then it shot up. And there's no way you can predict that because so many things can happen outside of your ranges of data. So you need to go research them. This sort of centimeters of handspan if you want to make predictions on it. And then this final slide, until I show something that's a bit more interesting, drawing conclusions. So discuss. This graph shows that the more pens you buy for the exam, the better you will do. Well, what do you think? The data looks like it's saying yes. I mean, there's people who have bought more pens. They've got a higher exam score. So are you just going to buy pens and get a good score? Well, to kind of show you this, I want to take you to this website. So this is a really good website. It's quite funny, and I will link it below so you can kind of scroll around and you can make your own ones as well with real data. But this is a website that kind of says just because things correlate does not mean that they causate. So correlation does not show causation. Causation means kind of like one thing causes the other. So we can say that the number of people who drowned by falling in a pool correlates with films that Nicolas Cage appears in. So you can see, as Nicolas Cage appears in more films, more people drown in pools. And I don't think we can really put that onto Nicolas Cage. But these two things do correlate at a 66% rate. Let's have a look at some others. So per capita cheese consumption, number of people who have died by becoming tangled in their bed sheets. This is a 95 almost % correlation. So if you start eating more cheese, very likely that there's going to be someone else in the world who's going to get tangled in their bed sheets and not make it out. Obviously that's a load of bogus, but this is real data and they correlate at a 95% chance. So going back to this, I mean, I'll show you the website a bit more. You can scroll all the way down, there's loads, and you can actually search up for your own, so discover a correlation. So you can click on that and you can kind of put two data things in there. They're all preloaded up. Let's see if we can find another one. So as more people eat chicken, the US imports more crude oil. I don't think that's a 90% correlation there. So concluding to this, yes, it looks like they correlate, but it's probably more likely because these people revised harder. They were more conscientious. You could say people who care more about their exams are going to bring more pens into it. I mean, someone who doesn't really care what they get is going to bring one pen that's going to break after 10 minutes and then they're going to stop writing. So just because the data seems like it links up, it probably isn't always going to be. And there's so many more external factors going on. I mean, there's a million external factors that are making kind of people getting married in Kentucky in America, and then people falling off a fishing boat. So, yeah, have a play around that website. I'll link it in the description of this YouTube video. Have a play around, but hopefully that gets the point across of just because two things are correlated does not mean that they cause each other. Bringing more pens isn't going to make you do any better. Alright, that's it. Cheers.